and you go and tell the other teachers what I've been up to, it's very hard for me to trust you. Jessica sold me out, apparently. Well, your name got divulged. So here's the tricky thing about when someone is telling something.
What happened?
All I heard was your name. Jessica sold me out. I stole Mrs. Goring's smart pen when she wasn't here last week. And Goring didn't even notice. Jessica's the one who brought the attention to it. All right, so last week, we talked about square roots. Remember, who can summarize our idea of square roots for anyone who might not have been here? Who can give me a good summary? What is a square root? Braylon?
The square root is when a number multiplied by itself gets values you're looking for.
So can you give me an example?
Like the square root of 4 is 2.
Yeah, the square root of 4 is 2. Now that one is a bit dangerous because it also works with addition. So be careful. Can you give me another one that works? Square root of 16 is 4. Or, what else did we talk about last week with square roots? -4. Thank you, Braylon. Thank you, Gabe. So square roots, as a reminder, are the result, or the number that multiplies by itself to get the number in question. So the square root of 16, square root of 25, those numbers work well. Now, last week we talked about sometimes this doesn't work very well, and that's where we're going to pick up our studies today. By the way, if anyone looked at this additional challenge, I forget if we talked about this last week or not. If we're looking for a number times itself to make -16, say that louder, Connor. Is that even possible? Brings us to here. So if you would please head your paper with 9.2.4 and then write on there real, can you put that in quotations? Real numbers. I have a red pill and a blue pill.
Use them as sunglasses.
So, real, right? What's real? We're in the matrix. Now, okay, so real numbers, right? Just like all things, numbers are classified, right? Like in different ways. Even and odd, composite and prime. So you learned about all these different classifications. But now we're going to tell you there's a classification for numbers called real. And the first thought in your head, at least in my head, is like, well, what the heck is a non-real then? Are there these like fake numbers floating around, like ghost numbers, spirit numbers? What are we talking about here? Now, let me alleviate some of your maybe concerns. Every number we have talked about, you guys gonna be okay?
No.
Every number we've talked about, that we've calculated, that we've dealt with, that you've typed into a calculator, all of those have been real.
Oh, yay.
Okay? So it's not like you've been working with the non-real. So before we dig into real, let's talk about the other actual classifications of numbers. I'm going to flip my screen so I can write with you to make your life easier and just write down the very simplified definitions. First thing we're going to write is a rational number, which hopefully we remember some of these because we've talked about some of these before. So please on your paper write down rational number. And actually, you don't have to say number. You can just put a little hashtag. Aside from that, it's a rational number, so it makes sense, right? If we think in the literary sense of rational. What does it mean mathematically when a number is rational? I shouldn't put equals, I should put is at the root of this word? Gwendolyn? Ratio. A rational number. Guys, I'm going to give you the simplest definitions possible. Can be written. Now, if you want to be fancy, mathy, what we start to say is expressed. Because it doesn't have to be written. So if you want to use the mathy word, say it can be expressed as a, what's another word for ratio?
Radio?
Fraction. Now here's where I make your life super easy. Write down the word irrational below that.
We just put an arrow up to it and then we say not.
I told you I'm here to make your life easy. Ear. Right? We know what ear does.
Yeah,
What does ear do to a word, guys?
Opposite.
Makes it opposite or not. So an irrational number cannot be expressed as a fraction. However, these are still real. We're not talking about non-reals yet. So these are still real numbers, even though they can't be expressed as a fraction. Take a moment to think in your head. Do you know any numbers that cannot be written as a fraction? Octavia? But that would become 3 and 78 over 100, and I could make that 378 over 100, so nope, that's rational. Connor? This is improper. Right, like 7/4. That's a... Fine. Throw this on your paper. Square root of 2.
She cheated.
It's okay.
So rude.
If you actually are looking for a number that when multiplied makes 2. Okay, well 1 times 1, crap, no, that's 1. 2 times 2, crap. 1.1 times 1, not big enough. 1, and we start trying, right? We got to do a number times itself. The square root of 2 is 1.4141213562. No, please do.
No, do tell us
Here's the trick with irrationals. And you need to write this down because otherwise we'll get to the test and you won't remember. It does not. Irrationals are all about not, bless you. It does not, we'll put a does out here, does not repeat. Does this form? No, it's unless this whole thing repeats, and I could actually go out the decimal strand and look at all these numbers, and it does not terminate. Which means, on the flip side, our rational numbers, repeating decimals, those are rational, actually. Even though they repeat forever, like 0.333333 forever, what's that as a fraction? It's 1/3, right? Can you stop, please? Do you hear yourself that you're doing that in the middle of class and you have like 20 people around you and an instructor trying to teach? Because it's really rude. And that's why I'm asking if you actually hear yourself. I need you to be self-aware, Quinn. Okay? I need to stop having to ask you to do this. Because at least once a week, normally more than that, I got to ask you to stop like banging around. Make it like, I need you to be self-aware. Any number that repeats or terminates, doesn't repeat, can be written as a fraction. It might be a big, messy fraction, or it might actually be a nice, clean fraction, So if you remember back in, I forget what chapter it was, I gave you guys fractions like that are a giant mess of repeating digits. Anyone remember what that is? I'll make this worth a piece of candy. I'd make it worth money if I had money to give away. 14, 28 are both multiples of 7. The nice fraction 1 over 7 comes out to be a decimal expression that never, ever, 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 ever stops. But it is still rational because it can be written as a fraction. Rational versus irrational, okay? The most famous non-rational number, or irrational, pi. It never repeats and it never terminates. And we've been investigating this for a very long time. We have pi out to, I want to say, billions of digits now. Like, it was millions, but we keep calculating pi because there are millions of numbers that come after that decimal. It's never repeated itself. And it has not stopped. So it's not going to. There's actually a mathematical proof that shows why, because pi hasn't stopped yet, it never will.
What is pi?
It is the ratio, and this is worth talking about, it's the ratio of circumference to diameter. If you have a perfect circle, that division never stops because how the numbers work together.
And it's not a very special number, it's just right there on the number line in between 3 and 4.
So, as Marley already gave to us, Olivia, you guys switch seats now, too. Good. Square root of 2, right? That is an irrational number. It is not nice. You're gonna need a calculator for this. Try these 3, and actually, more so than that, if you get done with those 3, move on to 101. Let's look at these different problems, figure out what do we think. Do they terminate, do they repeat, or are they irrational? Remember, if it repeats, it's rational. If it terminates, it's rational. By the way, guys, we need to have our calculators come back. I'm missing a good deal of them. So you can check your lockers and backpacks and stuff. Yeah, and so those are school sets. You can't just buy a yellow TI-30 on your own. These pink ones, you can buy a pink TI-83 on your own. So we're really just operating on trust. Not a yellow one.
Why not?
Well, they're at least sold in packs of 10 because they're made for schools. The yellow calculators are school calculators. Schools somehow got coded with yellow, I think because buses are yellow and other things. When people make stuff for schools, they should only make it yellow.
Pencils are yellow.
Pencils are yellow. Now, remember, we can do positive or negative, but we're going to not talk about the negatives right now. If I type in radical 6, ooh, by the way, Drew, do we know where the radical symbol is on our calculator? It's right above the x squared. So you have to hit the second button and then hit your x squared button, and that will put in the square root symbol, which last week we discussed makes the radical, or is called radical. That's what the symbol's actually called. The operation is square root. What is square root of 6.25? What do you get?
I use
2.5 or 2.25?
2.5. 2.5. 2.5. It's 2.5.
5.2.
Yes?
Yes.
Double check it if you need to. 2.5. Now, you might not need a calculator to do this one. Square root of 100?
1. Wait, no.
Square root of 7.
2.6575131.
Now, depending on your calculator setting, if you go into mode, whether you're in classic or math print or whatever, will determine whether it spits out your decimal answer or whether it actually just cycles you back and gives you radical 7 as the answer. That's your calculator's way of saying, like, nope. It's like when my wife came over and I was watching the basketball game last night. She was like, here's the dog pills, have fun. And I was like, no, not right now. I'll do that later. Like, sure, but no. This is your calculator's way, the pills that we had to give our dog. This is the calculator's way of saying no.
No.
Like, this doesn't work. Thank you, come again, try something else. So, what can we say since we got 2.5 as our answer here? Is it rational or irrational?
Rational.
Rational. What can we say here? Rational. And what can we say here? Irrational.
It's in here.
Now, let's make predictions. Put your calculators down. Hands off. Do we think these values are rational or irrational? Some predictions might be easier than others, but I need you to back up your prediction with a why. So, Marin, what do you think? -5 over 9. Would it be rational or irrational? What are we asking ourselves to determine rational or irrational? Like, what do we say a rational number is? Let's just remind ourselves of that. Can be expressed as a fraction. So, sorry, did you say rational or irrational?
I'm irrational, sorry.
Why'd you, like, shake your head and like, oh, wait.
Because rational can be expressed as a fraction, and that's shown as a fraction.
This is already expressed as a fraction, right? So if a number is presented in fraction form, it's rational. It's already there. We don't even really have to think about anything else, right? Yeah, it's done. So, Peyton, what do you think about radical set? Wait, we just did skip that. 21 over 4.
It must be irrational.
Yeah, it's rational. It's improper, but it's rational. I also don't like that we call it improper. That makes it sound bad. Improper fractions are fine, guys. Olivia, what do you think about negative square root 15? And we're just predicting, right? So let's think, what's 3 times 3?
Yeah.
9. 4 times 4?
12.
16. Ooh, wait, we jumped over. So it would be between 3 and 4, whatever it is. So your prediction is irrational. We'll come back and we'll test that. Pi squared. Well, we just said that we know pi is irrational. What do we think about when we square an irrational? Hmm?
It's always 2 over pi, right?
No, it'll be pi times itself. Right, like pi times pi. I don't know about that one. Let's come back to that.
I think it's irrational.
You think it's irrational still?
Yeah.
Pi.
We still think it's
So think about this. I have an irrational number times another irrational number. Anyway, we said radical 7. Hold on, this is worth talking about for a minute. We said radical 7 was irrational. Right? Go ahead and write this down. And we're hypothesizing an irrational times an irrational. Now, if we make our life easier for a minute, what's the square root of 9? 3. So the square root of 9 times the square root of 9 is really 3 times 3, which is really 9.
Oh, it's going to be 7.
So wait, the square root of 7 times the square root of 7 is 7.
Are you sure?
Nani?
So wait, those of you with a calculator, grab it. Find your pi button. It should be just 2 up from the square button. And then go 2 buttons down, hit squared. What do we get?
Hit pi first, then.
Hit pi, then squared. Hey, Braylon, do you hear yourself? It is March of 7th grade year. I do not know why I'm having to ask these questions. So I get like 9.86, 960, 4401. So that doesn't, I can't quite tell, right? I don't know if that repeats or if it terminates or what it does. I don't know. But can we say an irrational squared will stay an irrational? No, because we just looked at radical 7. Right, radical 7 was irrational. Squared means times itself, and it became rational. So that's interesting. An irrational times an irrational became an... Well, it's not making rules, right? We don't know enough yet to make rules, but that's interesting. Okay, worth noting, worth talking about. Don't exactly know why yet, but worth talking about. Micah, what about 730 over 99? Rational. And thinking back to last chapter, Quinn, negative 6.4 times 10 to the negative second, would that be rational or ear?
It would be an ear.
Why?
Because you would, even though you would be moving the decimal point 2 to the right.
2 to the right?
Left.
2 to the left. Okay. So decimal bumps to the left, and this would become negative 0.064. So is it rational or ear? This is rational because, guys, the decimal stops. Right? These numbers don't keep going on. It terminates. And we could just put this over like 1,000 or whatever, and we could have our value. Yeah. I'm glad you caught me on that. So, what do you think, Mallory? Negative. Does that negative out front impact rational or not?
No.
Positive negative doesn't really impact rational, right? So, radical 76. Well, what's like 8 times 8?
8 times 8 is
64. 9 times 9?
81.
Okay, so it's between perfect squares. So it itself is not a perfect square. Yeah. We'd have to use a calculator and see what we think. I think it might be irrational. Yeah, I think I would probably have to agree with you. I would think it's probably irrational also. Try this on your calculator. Radical 42.25. A decimal square root. So, now what Mallory just said is because square root of 64 is perfect, square root of 76 happens in there, and then square root of... So this is 8. What is radical 42.25? Yeah, so now you're set in scientific mode. So that's why it's giving you the times 10 to the 0 set, just means 6.5. I can fix that for you if you want. You need to do in like regular, not scientific notation. So that, is 42.25 a perfect square? Careful. Think back to last week. What did we define perfect squares as? It's the result of multiplying what by itself? Be careful, an integer. But you're right, it cannot be a partial number. So this is not a perfect square But does it come out to be rational? Yeah, this would be rational. Can we jump to a conclusion that this has to be irrational? Not necessarily. So all because it's a not perfect square does not automatically make it irrational. Here we have a not perfect square. It's rational. So it's okay for non-perfect squares to come out to be rational, or sometimes they're irrational depending on what the number is.
Wouldn't that just be a perfect square? Because it'll be like 6.5, 6.5.
So a perfect square, as we just said, is the result of multiplying an integer by itself, not an integer, right? So I could do 6 times 6. That's a perfect square, 36. Negative 6 times negative 6. So those are both integers. Not whole, integer, because it can be negative. Remember, whole numbers can't be negative.
Okay.
Integers are whole numbers and the negatives and the opposites.
Sometimes when I do radical, some number, it will do number, radical, then.
So that's putting it into simplest radical form. Trying to decide if we want to do that. So to explain what your calculator is doing on some of those, put your pencil down for a minute. So Connor, if you type in radical 32, what do you get?
4 radical 2.
So when Connor types radical 32 into his calculator, this is what he gets. I'm breaking stuff up here. 4 is the perfect square root from what start number? Like, what do we take the square root of to get 4? 16, right? Can anyone relate how all these numbers work together? Dave? If I rewrite this as radical 16 times 2, is it the same thing? Yeah, right. 32 is 16 times 2. Now hold on, stick with me. Can I rewrite this Can I break up the multiplication and say radical 16 times radical 2?
Yeah.
Yes, because if I do the math, this is still the same.
Oh.
And then what's radical 16?
4.
4. Radical 2 is not nice, so we leave it as radical 2. This is what's called simplest, and you can write this down now if you would like. You don't have to have this learned this year. Simplest radical form. Simplest radical form. So it's not just radical. It's not just an integer. Excuse me, it mixes both. It uses 4, nice, integer, we know what it is. Radical 2, gross, irrational, we don't like it. Meh, leave it as radical 2. Other questions? Now this is looping back to some previous work. Jessica is wondering if 0.57 repeating, is rational or irrational. So she goes to a friend and she says, well, I know 57, like the first 57, right? 0.57. That's 57 hundredths. So she starts writing 57 hundredths, but then she's like, nah, I don't think that's right, though. So is 57 hundredths, that fraction, equal to that decimal? Who can talk to yes or no? Right? Why?
Because it's just 57. And it's just 57.
As opposed to?
100.
Yeah, but so like, that just 57 over the 100, why wouldn't that make the decimal we want? What decimal would it make?
0.57
Yeah, not repeating, right? So if it was just 57 over 100, it's not repeating. Can anyone remember? And this, we'll play like Who's Line for 1,000 extra points. How we rewrite a repeating decimal as a fraction. Mallory? Now be careful. It's as many 9s as we have digits repeating, right? So on your paper, please, let's remind ourselves 0.57 has 2 digits repeating. So it becomes 57 over 99. However many 9s are on bottom, we will repeat that many digits. So I need to take a moment. Now be careful, a couple of these are tricky. Rewrite all of those fractions in their decimal equivalents. Be careful, a couple get a tiny bit tricky. Now, we should not need to use a calculator here, so I should have said that from the get-go, but knowing the rule we just talked about, we should not need a calculator here. By the way, this is slated to be our last section. Yeah. I'm not sure. I'm still formulating all that. So I'm counting days backwards, essentially, from the test and trying to figure out how to plan stuff. So still today, because last week got a little wonky, but this is the last thing we do in Chapter 9. We skipped the rest of everything else. And to alleviate any fears you might have, this year you take the 7th grade math test. Next year, you'll take the high school math 1 math test. You just skip. So, again, I've had these conversations with some of you. At the end of the year here, like in like a month or so, we're getting pretty close, we're going to take a final. And I'm going to ask you as part of that final to write up what path you would like to take. Whether you want to stay on this path and like you're ready to do work like at an even more intense pace, because Mr. Hall goes fast and it's pretty intense. Or do you want to take a step back and just go into Math 8 next year? That's not a group decision, Octavio. It is for each individual person. So realize if you're saying like, yes, stick on this path, you're taking high school math next year. And you will be tested on high school math at the end of the year. But this year, no matter what, 7th graders are taking Math 7's test. That's it. It doesn't matter what class you're in this year. Next year, if you stay on this path, you'll skip over the Math 8 test and take the high school math test. Class, what's this become? 0.19 repeating, right? What's B become? 391 repeating. C becomes 0.3 repeating. Now, can I get a volunteer for D? Brady? 0.001. Ooh. If you wrote down 0.1 repeating, you fell in the trap door. It repeats as many digits as there are nines. There's 3 nines, so I gotta repeat 3 digits. And there are 3 digits up here. Every number has an infinite amount of zeros ahead of it. And also, if we want to be technical, an infinite amount of zeros on the other end of it. So when you have more 9s on bottom than you have numbers on top, you got to put in zeros to take up the extra space. So E is an easier one again, 0.524 repeating, but then F becomes what? Quinn?
0.019 repeating.
019 repeating. Be careful on those. Questions? I know my smart screen is angry today and wants to try to capture the whole kit caboodle. Okay. We have 4 minutes to talk about why this proof holds true. And it's kind of a deep idea, so I want you guys to put your pencils down for just a minute and just, like, stick with me here. Actually, that can stay there. So, you can read through what they have in the book, but the first time I got shown this, it kind of blew my mind. So, all through school, you get told things that are like, this is true, remember it. And you're like, okay, sure, because I trust you, you're my teacher. But at some point, you got to start asking why. Right? Like, and that's where I fell in love with math, is there's always a why, and there's always a set of rules that goes with it. If I tell you that some unknown number is 0.57 repeating, and you apply your rule, you know it's 57 over 99. But if somebody presses you and says, okay, show me why, like, well, my math teacher told me it needs that many 9s on bottom, that's a really lame justification. If you said because someone else said so, that's a really lame answer. So let's imagine if I start doing some algebra, and we decide we're going to multiply by 100 on both sides just to get this decimal past where we repeat. So then we have 57.57 repeating, and still there's an infinite amount of 57s repeating. And that's equal to 100x. Right? Are we still with me? Do you agree that I have not broken any rules?
No.
What do you disagree with?
Oh, I was saying, like, no, you haven't broken any rules.
So then, I really want to get rid of this repeating chunk. Right? Because that's what's screwing everything up. Do I have an amount in the problem that I'm able to take away that gets rid of the repeating chunk?
1x.
One of the x's. Because an x is the repeating chunk. So if I take away an x, over here, I take away 0.57 repeating. Because these are equal values. Okay, are we still with me? That then leaves us with 57 equals 99x. And from there, we have proof of why that repeating decimal becomes the fraction over 99. This will work with any amount of repeating digits. So if you were asked, and it wouldn't be this year, but maybe next year, to show a proof of how repeating decimals convert to fractions, this is it. This is your proof. Nice little 2-step, well, 3 if you count down here, and that's it. Questions? It's in your book, so you don't have to write this down and you'll review it next year. This is in your book. Go back to it if you want to, but aside from that, that is all the time that we have for today.
Does that mean that all decimals are
Every repeating decimal is rational. Because rational numbers repeat or terminate. If they don't do one of those things, it's irrational, right? If it does not repeat, does not terminate.